Okay, okay. So reduction of order, again, something that pops up several times in the chapter on higher order equations. And it comes down to this. For a second degree equation, or a second order equation, okay, in y and y prime and so forth. If we have one solution, which we'll call y1 of x, we can let y2 of x equal u of x, y1 of x. And hopefully solve for u of x. Having done so, then we just multiply y1 by u and we get it. And this word here should be and. Okay, just to illustrate a simple equation. Now, we can easily find both solutions of this equation just using the method that I sketched last time, that y equal e to the RT, you get the equation r squared plus 3r plus 2 equals 0. And the solutions are r equals -1 and r equals -2. So we know what the two solutions are. They're e to the negative x or 2, whatever, e to the negative x and e to the negative 2x. Let's pretend we only know one solution. And let's call this y1 and y2. Now pretend we don't know y2. Let y2 equal u times y1. And see what happens. Plug this into this equation. Okay, well, first derivative by the product rule. These are both functions of x. The u prime y1 plus u y1 prime. And here's our y double prime. So what do we get? Well, we get from y double prime well, we just write down this expression for y double prime here. And then 3 times the expression for y prime. And then plus 2u1y1. And that equals 0. Well, that's a lot simpler, isn't it? Not really. But if you look at what's hidden in here, remember your equation has a coefficient of 1 here, a coefficient of 3 here, a coefficient of 2 here. You have 2u1y1 here. And from this, you're going to get 3u(y1 prime). And from this, you're going to get u(y1 double prime). And notice that, and it's not u1 here, it's just u. Notice that you can then factor u out of the expressions that you get. And if you got a good eye, you can see that what you get after you factor out u is y1 double prime plus 3y1 prime plus 2y1. Well, y1 double prime plus 3y prime plus 2y is 0. So this term, and this term go away. Well, I'm going to write that out, but that's how you look at it. And that's the way you want to see this. And it's always going to be that way. Depending on time, we might well do the proof for the general case. Now, I'll also comment that this is a simple equation with constant coefficients. You don't need reduction of order. You don't always have constant coefficients. It could be a 3x squared y and a 2e to the negative xy, or 3x squared y prime and 2e to the negative, whatever. Okay, and you could even have a non-homogeneous part over here, and this is going to help us understand what to do there. Okay, well, looking at the algebra here. Make sure I've got this right. Yep, okay. I'm going to have to move this board over a little bit because of watermarks and stuff. So the video is going to be, no, yes. So we're not blocking some of this stuff. So, you know, I've just rearranged this so that I've got my y1 double prime plus 3y prime plus 2y1 equals 0, which equals 0. So now my equation It's just going to be this. And this is a first order equation in U prime. Now let's write that out. I'm going to try to squeeze it in at the bottom of the board. Just going to switch boards here. Okay, so the equation we get, and I'll just note that this term is 0, so we're just left with this. Okay, we get this equation. Now remember that y1 is already known. Y1 is e to the negative 2x. So anytime we're ready, we can substitute e to the negative 2x for y1. The other thing that we can do is notice that we don't have u here anymore. We just have u prime and u double prime. I keep writing u1s. Okay, we have u prime and u w prime. Okay, so just to make sure. Y1 is e to the negative 2x in our example. We have no u. Just u prime and u double prime. So let w equal u prime. Then u double prime equals w prime. The equation becomes, I'll write it this way, y1 w prime. There's y1 u double prime, but u double prime is now w prime. 2y1w plus 3yw equals 0. Or now obviously I can factor w out of this. And this, I think I've messed up something. We should have a y1 prime here. So I'm gonna have to fix that. Y1 prime, of course, y is e to the, y1 is e to the negative 2x. And the derivative of that's negative 2 e to the negative 2x. So 2 y1 prime is going to be negative 4 e to the negative 2x. And then the 3y is, and I'll write it out. Okay, now this should be starting to look like something you know how to solve. And of course, I'm going to combine these into just negative e to the negative 2x. But then what do we get? This is going to be a separable equation. It's going to be first order linear also, either way you want to look at it. Okay. Separable or first order linear. Now, in this case, the equation is almost trivial because to put it in standard form, well, whether to put it in standard form or not, let's go ahead and do the separable. If we put it in standard form of a linear equation, we're going to divide by e to the negative 2x. We're just going to get w prime minus w equals 0. And something I don't like about that because it doesn't seem to give us the right solution. Let's see. Okay. I'm going to put it, though, in the order of a separable equation. So if we put it in the order of a linear equation, you got a w prime and a p of x w equals 0, homogeneous. And your solution is totally straightforward. Although I think the solution is e to the x and not e to the negative x, which it shouldn't be. But yeah, got a sign wrong or something. Anyhow, that aside, look at the structure of what we got. So we put it in the form of a separable equation. And that's going to be I'm debating about whether to divide that e to the negative 2x out of there or not. And I guess I do want to divide it out of there. And I'm going to just kind of skip that step that clearly divides out. And e to the negative 2x is never 0. So we don't have to worry about that. And we get w prime equals w. So dw over w equals dx. Integrate both sides. And we get natural log of the absolute value of w equals x plus a constant. So that w equals c1 e to the x, which is almost right, except we get, oh, never mind. Well, no. That's w. We got to get y1 out of that. Remember the w prime equals y1. And we get, if y1 is derivative of w, sorry, if I wrote that wrong. Just wasn't looking right. It's y1 prime equals w. Duh, where to do it? Yeah, let w equal u prime. Actually, it's u, not y1. That's going to work out. I was leaving out a step when I was looking ahead. Okay, U1 is U prime is W. So U is the antiderivative of W with respect to X. So U is C1 e to the X. Let C1 equals 0. So U equals e to the X. Thus, well, where are we? Let's make sure we understand where we are in terms of this solution. We started off with this equation. We use this solution. Since we know this solution, we can find another solution by letting y2 equal a u of x times y1, as we say here. And then we work it through. We see a bunch of stuff goes away because we can match up some of these terms with the original equation, write it in this form, and this is the original equation, it has to be 0. That's always going to happen. We're left with this. We take this equation and we recall what y1 is. We note that there's no u, just u prime and u double prime. So we can write this in terms of w equals u prime. And then we do something pretty straightforward. Similarly, we do the integrals, and we get u. Well, our original premise was that y2 is u times y1. And that's e to the x, e to the negative 2x, and that's e to the negative x, which we already knew was going to be our solution. And now we're done. Okay, well, it's easy to prove if you want to just write an equation with just plain old, a p, or call this ay prime and by, and work it through, and you prove that the same sort of thing happens all the way through, and you get your second solution. So it's not a very interesting method if you have constant coefficients, because you can always solve the equation for constant coefficients. And you haven't actually gotten to where you're solving one, but I illustrated it last time by letting y equal e to the rx, plugging that in, getting a quadratic equation in this case, which you can easily solve for r, giving you your two solutions, et cetera. So you don't need this. If these aren't constants, then it's real good to have this method. And things still line up the way they do, whatever your coefficients of y prime and y are. So I'm going to go ahead and work it out. For that case, now even the textbook tells you, well, what I'm about to do is going to give you a formula that replaces all of these steps. Well, that formula is a great shortcut, and it tells you in the text, I don't think it's in the problem set, I know it tells you this, tells you, well, let your instructor tell you whether you need to work through all these steps or just use the formula that we're going to get. And I'm saying, most of the time I'm going to want you to work through the steps, but you also should see how to use the formula because it saves time. But I think you need to understand the steps before you do the formula. because then you understand stuff that comes later with variation parameters and other stuff much better. Also, just like getting that dam torn out and finally seeing that, the pulse saw will do the job, even though it won't poke the slats loose. There's an aha moment when you understand things that you wouldn't otherwise. Okay. In this case, any fool would have figured that out quicker than I did. But okay. So okay, let's move on. Okay. Okay, got this. And y2 of x is a solution. Okay, so here's your equation. Instead of 3 in front of y prime, we got p of x, which is a function of x, q of x, and that's in front of y, not just I often forget to do that. Okay. First of all, let y equal e to the lambda t or e to the lambda x, whichever, is not going to work if these are non-constant. It only works for the constant because if they're constant, you get a characteristic equation, a quadratic equation in R. Okay, letting y equal e to the RT. Clearly, if you have functions of x, you're now going to get something besides that characteristic equation, that quadratic equation, and it's not going to be useful to you. Okay. In this case, let's let this be y1 of x. We want to find y2 of x. And let y2 equal u y1. And the derivatives are no different. Writing this out carefully because I'm prone to errors. So just be careful. Clearly, we're going to get a u double prime y1 and a u y1 double prime. But then when we do the derivative of y1 here, we're going to get a u y1 prime. We do the derivative of u here, we're going to get a u prime y1 prime. And then we need a prime in the u. Okay. Then our equation becomes, write it out carefully because I don't, we're going to have to fix it. So far, it looks a whole lot like what we had before. Put the p of x out in front. Okay. Now the same terms are going to go together to give us the original equation. which is equal to 0, so we can get rid of it. In other words, q of x times u y1, if we factor out u, is going to give us q of x y1. This term, I hope, multiplied by p of x is going to give something that if we factor out u, we get p of x y1 prime. And this term here, if we factor out u, is going to give us our y1 double prime. So what we end up with is these three terms, here, here, and from here, plus a bunch of stuff that's going to be 0. And that's going to be u times y1 double prime Okay, so there's everything. It's pretty obvious what we've done. And just like exactly what we did before, except we're using some extra symbols to represent coefficients, functional coefficients of y and y prime. Well, all this is still 0 because this is just your original equation, which is equal to 0. And you're left with u double prime y1 plus 2u prime y1 prime plus p of x u prime y1 equals 0. This is the differential equation again in u1 prime and u prime and u double prime. So again, we're going to let w equal u prime, and we get w prime y1 plus, and let's go ahead, and I'm going to just get a little fancier, just not all that fancy, just commutative law here. Okay, y1 w prime, because u double prime is, or w prime is u double prime. So there we have it. And then it's plus y1 prime w plus big P of x y1 w equals 0. And this is, again, a separable equation in w. Now we simplify it one step. And what I'm going to do is I'm going to take my w terms and throw them on the right side. And I'm just doing what you would do with any separable equation. Okay, so we have this. And then it's going to be convenient to have y1 in the denominator over here. So we just got w prime. So we're going to divide through by the y1 prime. giving us y1 prime over y1. And of course, dividing this term by y1, y1 goes away. Now this is separable. We got dw dx equals negative quantity y1 prime over y1 plus p of x. And it's dw over w. Right through by the w, then put the dx over here by the magic of pretending it's algebra. Okay, so we have this so that the natural log for the absolute value of w is equal to the integral of, I'm going to separate this into two terms. And I get this. Well, y1 prime is like dy1 dx, and you multiply it by dx, and you get dy over y1. It's going to give you a natural log of y1. And this is just going to be integral negative p of x dx. Okay, well, let me just copy that. Here and complete the solution. So that everything works out. The only thing you're not going to know is what this integral is. And this, in a minute, is going to give us a sweet little formula for bypassing all semblance of insight and using a formula, which you know very well from having had a couple of other courses from me. I don't like it. Okay, not until you understand the steps. Now, sometimes it's necessary, but in this case, it's pretty straightforward. Once you understand how these things work out. And this whole process of reduction of order, it gets boring after a time. And at that point, when it gets boring, when it's the same every time and you know it's going to be the same and you know what the process is, then by all means, save yourself the pain and use the formula, but not until that point. Okay, so we then exponentiate to both sides and we get w equals e to the negative natural log of the absolute value of y1 minus the integral p of x dx. And of course, e to the negative natural log of the absolute value of y1 is, well, I think I've got room, I might regret. Using up that much space, but I think I can handle it. tend to overestimate my ability to do that. They got I forget what the name for the effect is, but it's like the less you know, the more you tend to overestimate what you know. So take that for what it's worth. As far as my use of board space, I know that it's problematic. Okay. Well, this e to the negative natural log y1 is 1 over the absolute value y1. And then we have this, and we're pretty much done, except what we've got here is w, not u. As before, and I'm not going to write it out because I do have the idea that I'm going to run out board space. Okay. So now u is this. But of course, wherever it is, all the way back here, remember that y2 was u, y1, and y2 is our goal. So we've gone through u, and we had to go to w and then get back to u, and now we've got to get all the way back to y2, but that's really easy. Y2 equals u, y1. Finally, y2 equals u, y1, and we've got our new solution, at least in integral form. Making sure I've got everything written down. I think I have it written down correctly. So we have y1 times u with u equal to this. That's y1 times the integral of e to the negative p of x my dx was a little high there. Looked like part of the exponent. Okay. So this is our reduction of order formula. I say don't use it until you know this process backwards, forwards, and inside out. Okay, because among other things, critical time, you might forget the formula. Then you can't think things through. If you can think them through, you're better off, even though you can always Google the formula, it's always there. You can always get the answer, but there's insight that's lost if you bypass the process with the formula. So I'll say avoid the formula until the process is mastered. And write it nice and big. It's y1 times the integral of e negative p of x over absolute value of y1. And remember that the absolute value of y1 never mind. Didn't say something wrong. Okay. That's it. That's reduction of order. Okay. So Was that fun? Looking at the homework now, just to give you an idea of what to expect. You have problem one is constant coefficient problem, except that reduction of order is going to be very useful because you have a second order equation with repeated roots. And I think I might go ahead and do one of those. I had from, I've got an error here. Can't imagine how that happened, but I certainly can imagine that it would. There's an error. Guess this should be y1 squared. Now, how did that happen? No. Somehow we end up with a y1 squared here. And it's under the integral sign. Okay, two things. I see what's going on. Okay, well, first place, no, those are negative signs, but the negative signs get subsumed. So that's not right. That's not wrong. I'm going to work through one and then I'll figure out where the error is. Okay, so there's an error here. This term should be y1 squared. When I work through this last example, which shouldn't take long, it should be okay. Okay, well, I'll fix that, and then I'll see what went haywire here, hopefully. It isn't until number 3 that you get an equation that doesn't have constant coefficients. And number 3 and number 4 and number 5 all say to use the reduction of order formula. I really don't want you to do that unless you have to. If you have to, admit it and we'll work some out. Okay. If you can get it using the formula, then you can get the answer, which is often enough for an engineer, but it's a good idea to have deeper understanding. So kind of do that. Okay, one more illustration then. As soon as I find a little bit of board space. Got a little bit there, got plenty there. Have I used the backs of these boards? No, I haven't. Good. Okay. So let's take the equation here. When you factor this, well, when you get the characteristic equation, if you remember what I did last time, let y equal e to the RT, the characteristic equation is r squared plus 16r plus 4 equals 0. That's r plus 4 squared equals 0. R equals -4. That's only one solution because you have a repeated root here. So we know that e to the -4x is one solution. We know since it's a second order equation, you got to have two linearly independent solutions. Two solutions whose Wronskian is non-zero. Well, if you let y2 equal u y1, as before, you're going to get y1u double prime going out on a limb here. I'm doing this in my head. Okay. Now, hopefully this is correct. I know this much is right. And I'm going to get three terms there, and I've got to have this and this. So I think and hope this is right. This is 0. So now you get y1 u double prime, but y1 is e to the -4x. And something doesn't feel right, but that's probably just my imagination. So I think we come out like this. If we don't, it's going to be similar. The process is going to be familiar if you've worked through the other steps. And this is then this. Which gives you then, so it doesn't look like it's going to work out right, but let's go through it. It's U prime, but now it's W. Okay. And this is going to be separable. And you're going to get finding out to e to the negative 4x. Rearrange this, integrate it. Negative 20 can't be right. We don't need the integration constant because when we exponentiate both sides, that just becomes a constant out in front. And if we have a solution, any scalar multiple solution is going to be a solution. And we shouldn't be getting e to the negative 20x. We should be getting e to the negative 4x. So something's wrong with one of my calculations or derivatives here, and that's going to have to be fixed. But the flavor of the solution goes on, so that you use the integral w, which will be negative e to the negative 20x over 20, and y2 then is I've messed up something. Probably up here where I tried to skip a step. Anyhow, we're out of time. This can be done, be a good exercise. We have one just like it in the text. If you do this step to here carefully, then it's going to work out a lot better. Yeah, something's messed up. Anyhow, there you have it. Fairly straightforward method until it gets complicated. Okay, so I'm going to stop the recording.